left last time. And as I mentioned, sort of overall, we spent a bunch of time in the initial part of the semester going over all these math of especially geometry and calculus of these scalars, vectors, and tensors. And getting real comfortable with that is going to help us with understanding this kinematics business of how things are deforming. That's what we've been studying in this chapter 2. Another quick note, we are not really assuming small deformations in this chapter. Throughout your undergraduate studies, I believe most of you, almost all of you, would have made the assumption that strains are small, right? That deformations are not too big, so we can treat the structures as linear elastic structures. In this chapter, we are not making any such assumption. Deformations can be as large as you want. And we are going to try to understand how we can describe, first of all, these deformations, and then compute strains, deformation gradients, and all those things that you have already computed in the past, but now in the setting of finite deformations, which is large deformations really, and see how to extend those concepts to 2D and 3D cases as well. So very quickly, we've been looking at these deformation maps, which as I said, you remember that this deformation map really is the solution to our problem that we are looking for. Right? So if you remember back from chapter 1, when we set up the problem of structural mechanics, we said that we have some body, we have some loading, some boundary conditions. What we want to find is the displacements, the strains, the stresses, damage, etc., whatever we needed. Displacements here are very tightly related to the deformation map that we are talking about, this deformation map, because displacement is nothing but the deformation map, that is the final position minus the initial position. So if you know the map, you know the displacements, right? If you know the displacements, you know the strains. If you know the strains and you know the material properties, you can find the stresses. So really, it's deformation map that you want to find in a structural mechanics problem. If you find the deformation map, you can compute everything else about the deformation and the structure response. So what we said was we look at some examples of what this deformation map might look like. And for now, we are going to assume that we know the deformation map. Obviously, this is something that we want to finally find, and we'll see procedures of how to do that. But for now, let's assume that we know the deformation map, and let's try to understand what it really means. So we looked at examples of translation. Just add the same displacement field to each and every point of the body, and you get to a new position. We looked at uniform expansion. We looked at approximate bending. We looked at an exact bending of a cantilever beam. These are all examples of deformation maps that take points in the undeformed black configuration to the deformed blue configuration. You can map each and every point in a one-to-one manner in that way. All right, so far so good. Then we started to look at, well, now that we have this 2D or 3D deformation map, how do we generalize the concept of strain from our 1D understanding of delta L over L to something that works for arbitrary shaped bodies and in arbitrary directions. So we said, okay, since we understand the 1D concept of strain and stretch, we will try to generalize that 1D concept by imagining 1D objects within our 3D body. What are those 1D objects? Those are curves. So last time we looked at these two simple curves C1 and C2 in the black configuration and their deformed curves in the blue configuration. And we said really that if you know the parameterization of the black undeformed curves and you know the map, then you can easily find out the parameterization of the deformed curves. All you have to do is to plug in the value of z in terms of s here, and you will have the value of x1, x2, x3. And so it's really just that simple. We also looked at how to generalize the concept of stress. Now that we can track strain and stretch along individual directions, along individual curves, let's try to figure out what that means in an arbitrary three-dimensional direction. So we said, okay, we'll just use the same concept of tangent vector to a deformed configuration is equal to stretch at that location times the undeformed tangent vector. That black curve goes to this blue curve. If you pick some point that is corresponding to some parameter, let's say s equal to 0.25, we are here on this curve. Then the same s in the deformed curve, s equal to 0.25, will give you dx over ds will give you the tangent vector to the same curve at the same point in the deformed configuration. And the ratio of them, dx over dz, will be the stretch. So this definition of stretch allows us to relate the undeformed tangent vectors to the deformed tangent vectors for a specific curve. Then we said, okay, how to generalize that for any possible curve in any possible direction. We came up with this long expression, which I just pointed out was just a chain rule. And that brought us to this tensor F that we created. This is the F components of the F tensor. This is the components of the undeformed tangent. This is the deformed tangent. So F is a tensor that takes undeformed tangent vectors to deformed tangent vectors. Just like any other tensor, a tensor acts on a vector to give me another vector. This particular tensor, a very important tensor, acts on any undeformed tangent vector and gives you the corresponding deformed tangent vector. And I think about this is where we were about last time. We were trying to figure out what the components of F look like and how to write that long expression, that long matrix expression in a short form way. So I hope you can see that partial xi, partial zj, partial ds, the j is repeated here. That immediately means that we have three terms. And since I can take values 1, 2, 3, and I is also repeated, we get the three terms of the vector. So this short form way is the same as writing this long equation out here. I hope you all see that. And this immediately tells us that the components of F can be written in this manner that I already wrote up here. Now, a lot of people define F in different ways, so I'll write some of those definitions here. One definition is gradient with respect to z of the deformed locations. And since that's a tensor, I'll have this huge tilde under this as well. Alternatively, you might write it as something that I already wrote on the previous page, x dyad with grad, right? So this F is a gradient of a vector field. Gradient of a vector field is nothing but is a tensor field, right? So F is indeed a tensor field. And this gradient is, of course, with respect to z. That's one way to write it. And with slightly ambiguous notation, some people write it as partial x, partial z. These are all the same thing. They are all referring to the exact same thing. Okay. Now, sometimes people would also write the same thing in terms of phi. So people sometimes also write that as the same, just replacing x with phi. Partial of phi or phi of z, tensor or dyad with gradient of z, which is equal to partial of phi of z, partial z. So lots of different people write this tensor f in lots of different ways, but essentially you should understand that it's the same thing. That what we are doing is that it's the components of partial derivatives of xi with respect to xj, and with the tensor basis ei dyad gj. Essentially, it is the components of this matrix, partial xi with partial zj. Um, and since I'm writing it in components, I'll write that again here. Partial xi, partial zj, ei dyad with gj. Um, so anybody remember why we had these two different basis vectors here? Why ei dyad gj? What is e? What are the e vectors and what are the g vectors? Say that again. We assumed that they are in the same direction, but you're right, they are different coordinate systems, because what we said was for any deformation process, I can define the undeformed body using one coordinate system, that's E1, E2, E3, and I can G1, G2, G3, and the other deformed blue configuration here using the E1, E2, E3 coordinate system. So for simplicity, we said we will assume they are both in the same direction, but this is not necessary. So really what F does is it takes, I'll write it in this fashion right now, and in that I'll show you that interpretation as well. Before I do that, it's the same as partial phi I, partial zj, ei dyad gj. So what we are saying really is that this F tensor takes arbitrary unit vectors from the undeformed configuration to the deformed configuration, right? All I did was write it as dx, the deformed tangent vectors, is equal to F tensor acting on the undeformed tangent vectors. So this interpretation is very useful. This dx is equal to F dz. What's really happening is that if you go to a particular point, go to any point in the undeformed black configuration, in the neighborhood of that point, you have infinitely many vectors, unit vectors, right? That's the black sphere that I've sort of drawn out there. Now, those infinitely many unit vectors, you can think of them as tangent vectors to some curve, correct? There are infinitely many curves passing through that point, and those infinitely many black arrows that we have are tangent vectors to those curves. What F does is it takes the undeformed tangent vector to the corresponding deformed tangent vector, which is shown as a blue ellipse up on the deformed shape. So this black sphere becomes this blue sphere in the deformed blue ellipsoid in the deformed configuration. And if you draw all of those corresponding arrows, this is the small black sphere blown up here. This is the blue ellipsoid shown up here. Pick any one of those. This F tensor acts on that and gives you the new tangent vector. Okay. So this is a very useful understanding of what F does. F captures the state of deformation in all possible directions at a point. And if you express F as a field, then it captures the state of deformation at each and every point in the body in all possible directions. So F is a real important tensor field. Okay? We had the map, which was ultimately what we wanted to find, very important quantity. This F, which is the gradient of that map, right? It's the gradient of a vector field. That is also one of the most fundamental quantities in mechanics that we will need. Let's see if I can get my cursor back here. Not so much. Something. Okay. All right. Let's take a look at some of these examples of this F tensor field that I'm talking about. We had this simple example of translation, right? Maybe take a minute or so and let's do all of these. First, do it. I'll do one and then you can do the rest of them. So for this particular translation map, this can be represented, this Z can be represented as Z1, Z2, Z3, and plus a constant vector U1, U2, U3 that does not. So constant vector means the components U1, U2, U3 do not depend upon Z. That we are adding the same thing. So F is a tensor field that is the gradient of this. So we can write that as partial of z plus u, again with some ambiguous notation here, but in terms of components, what we are writing is the partial of xi and zj. So z1 plus u1 derivative with respect to z1, what is that? Okay, 1. That's the first term. Z1 plus u1 derivative with respect to z2, 0. Similarly, derivative with respect to z3 is 0. The second term is z2 plus u2. z2 plus u2 derivative with respect to z1 is 0. Right? z2 plus u2 derivative with respect to z2 is just 1. 0. And similarly, the last row you can see is derivative of z2 plus z3 plus u3 with z1, z2, z3. The first two would be 0, and only with derivative with respect to z3 would be 1. So what we get here is the identity tensor. Identity tensor. How can we interpret this fact that for a translation map, the deformation gradient that we got was an identity tensor? What is the physical meaning of this? It's not being deformed, because you see this interpretation of f that we came up with, deformed tangent vectors are equal to f times undeformed tangent vectors. We have seen this exact relationship very shortly back here, that deformed lengths are equal to stretch times the undeformed lengths. So that stretch, which really just measures the final length divided by the original length, that stretch is the same quantity that we are talking about here. Here, f serves as the stretch in arbitrary three-dimensional problems in arbitrary three-dimensional directions. So indeed, since there is no deformation here, each and every tangent vector is not being stretched. So when f is identity, that means lambda, or the stretch, is 1. That initial length is the same as the final length. That's a simple example of a translation. I'll let you do some of these other ones, and then we'll compare notes. Let's just do the second one, and then we'll do the third one together. How about the f for the second subcase here for uniform expansion? What would f be for this case? Alpha times I, right? So indeed, that is represented by alpha, alpha, alpha on the diagonals. Everything else is 0. And the easy way to check that is that this vector or this map is simply alpha times z1, alpha times z2, alpha times z3. So when we take the first component alpha z1 derivative with respect to z1, we get alpha. Alpha z1 derivative with respect to z2, z3 are 0. And the same thing for the second and third terms. So I hope if I give you a map, you can very easily calculate the f tensor field. And keep in mind that this is a tensor field. It is the same exact f at each and every point in the body. Okay, it's the same exact tensor at each and every point. Let's do the third one. Approximate bending of, this is a map that we've seen before. The map's given out here. The f tensor field would be given by the derivative of the first with respect to z1, what would that be? 1 minus delta 1 over L, not L1, just delta L, delta 1 over L. A derivative with respect to z2, z3? Okay. And the second component, derivative with respect to z1? Negative delta 2 cosine of z1 pi over L times pi over L. Agreed? And derivative with respect to z2? Just 1. And derivative with respect to z3 is 0. Similarly, the last row, derivative with respect to z1 and z2 is 0, and derivative with respect to z3 is 1. So that's the tensor field that we get for this particular problem. Note, in this particular case, the tensor field is not constant. It means the tensor f is different at different points of the body. Okay, and there is a good way to visualize that. I already wrote a MATLAB code to do that. So let's see how to do this, how to visualize these things. And I'll post this MATLAB code on Blackboard so you can play with it. So here is, get my cursor back again. Yeah. So I won't go through the code. I'll let you do that and try to understand how it works. But let's play, or let's just run this code. And what I am showing you first of all is that map. That black bar is the undeformed beam. Okay. If I apply the deformation map to that, I get this blue configuration up here. And it clearly maps one point, each and every point to its corresponding point. I've not done anything with the deformation gradient yet. That was just displaying the map. If you want to show it in different plots, I'll change the subplot option to 1 and run it again. And now I have this figure, this plotting the same thing, just in 2 different figures. And now I will turn on this option that says draw the F tensor field. I'll change that to 1, and it should draw my tensor field. And let's take a look at what that looks like. All right, there we go. So in the undeformed configuration, we have all these circles. What do these represent? This is the undeformed tangent vectors, that black sphere of unit vectors that I've pointed out, right? At each and every point of the undeformed configuration, I have a set or infinitely many possible undeformed tangent vectors, okay? If you go to its corresponding point, let's pick at the top left corner. There is a black sphere here which goes and becomes a blue ellipsoid, which means that the corresponding point that was up here has been transformed to a blue ellipsoid in this left corner. The same ellipsoid at the center of the beam is not twisted in that direction. If you can see, it's only compressed in the horizontal direction. Why? Because we know that the map, what it is doing is it's shrinking the length of the, not shrinking the length of the beam, but essentially compressing the top fibers up here. Okay. If I similarly look at the top right ellipsoids, these top right ellipsoids are pointing in the other direction. So this code can help you visualize any deformation map for a given particular body that you want. You can play with this and try to understand. The whole purpose of this is to show you that F, the tensor, is actually a field. It changes from points to point, just like stress tensor or strain tensor is a field. It changes from point to point, and there is a nice way to visualize it. All right, so what I did there was just to plot that black configuration, blue configuration, and I plot this deformation gradient field on that body. Any particular questions on how we are doing this computations? Okay, so all we did was just took the derivatives of the given map and we just plot it over the body. So all that is fine and good. We are still just dealing with definitions. Let's see what some of their physical meanings are. Okay. Now, I said on the previous page, which was, I think, maybe here. Nope. Here. On the previous page, I said that if you have a curve, you can find the stretch, or we define the stretch lambda to be the quantity dx, dz, dz, ds, right? That lambda relates those to undeformed and deformed tangent vectors. We didn't say how can we find lambda. Okay, that was just to define the quantity stretch at an arbitrary point in the curve. Let's see how we can find this lambda. So now let's consider at a given point in the undeformed body, I have all these possible tangent vectors, undeformed tangent vectors. When f acts on it, it gives me all the corresponding deformed tangent vectors. In some directions, there might be compression. The tangent vectors get smaller, or the curve in that direction gets smaller. In some other directions, it might get elongated. Some directions don't change. So this F tensor will completely capture all the possible directions. If I want to find out what is the stretch along a particular direction n, the way to do that would be to try to figure out what is, try to relate this n with its corresponding mapped n. Okay, so maybe what I'll also do here is I'll draw a curve, a black curve. So maybe this is like some black curve to which this n vector is a tangent at that point. Okay, and the corresponding blue curve is maybe something like this. So this black curve deforms to this blue curve at that particular point. The tangent, undeformed tangent vector is n. The deformed tangent vector is f acting on n. I hope that's something that you're comfortable with. The undeformed tangent vector is n. When f acts on it, the deformed tangent vector is just simply f acting on n. Okay. Now the stretch will be defined as f tensor acting on n magnitude divided by n magnitude. Do you agree with this? The stretch at a point along a curve where the undeformed tangent vector is n and the deformed tangent vector is f acting on n, the stretch is simply the length of the deformed tangent vector. This guy up here is nothing but dx ds magnitude. And this guy down here is nothing but dz ds magnitude, which is what is the definition of lambda, correct? Now, the undeformed tangent vector, since we are assuming that we will take ds to be measuring the length of the curve, we can easily pick a parameter s that actually corresponds to the length of the curve. So n would be a unit vector. Magnitude of n we can set to be equal to 1 without loss of any generality. What we get then is that the lambda n is equal to f acting on n magnitude, which is nothing but, and I'll have to move some stuff here, which is nothing but the square root of f acting on n, that vector dot with itself. Do you agree with that? The numerator is f, n is a vector. Tensor acting on n is a vector. The magnitude of that vector is simply that vector dotted with itself and the square root. All right. This quantity that I have in the brackets, it can be written in a slightly different way using in this form, n dot with f transpose f times n. What am I doing? I'm treating, excuse me, I'm treating this F tensor. I'm treating this F tensor as I'm using the definition of the transpose of a tensor and taking this F tensor to switch the order of those two, right? This tensor acts on a vector and is dot product with another vector. I'll switch the order of those two vectors. So Fn comes on the right hand side. Fn comes on the right hand side, and this n goes to the left hand side out here, and I just do a F transpose using the definition of the transpose. Okay, that's all I did here. There's a benefit of writing it in this form. This particular quantity F transpose F is something called a tensor C. So where C is equal to F transpose F. This is yet another very important quantity deformation tensor called Cauchy-Green deformation tensor. And we'll see what is the benefit of doing F transpose F in a little bit. But what we have defined up until now is a map phi. If you have the map, you can find F deformation gradient tensor field. If you have F, you do F transpose F and you get C. Let me ask you this. Is C a field or a single tensor? Is C a field? So if I have this body, I tell you that the deformation map is something like this, then we said that you can find the F tensor at each and every point of the body. F is definitely a field. F transpose F at a given point, that would give me C. At a different point, it would give me a different C. So C, this Cauchy-Green deformation tensor, is also a field. It of course differs from point to point because it's dependent on F, which itself is a field. But essentially, if you want to find the stretch at a particular point of a curve, find the tangent vector at that point, take F acting on that tangent vector, divide that by, take F acting on n, divide by n, that would give you the stretch. That's one way. Or you take the F tensor field, take F transpose F, you get the C tensor field, and then you do n dot with C n. That will give you the square of the stretch. So if you take the square root, then you'll get the stretch along a point. Here's why one reason why C is a good quantity to evaluate. Can you tell me whether F would necessarily be symmetric or unsymmetric, or can we say anything about that? Is F symmetric? F is symmetric. How about, let's take a previous example. This F, not symmetric. F need not be symmetric. Okay. If you have an unsymmetric matrix or a general any other matrix, if you do F transpose F, would that be symmetric? That would. Say it again. Not minus, but so actually I'll come to that. There are two different ways, F transpose F and FF transpose. There are two different deformation tensors, but yes, F transpose F would be symmetric. You take any matrix or tensor, transpose with itself would be symmetric, and the fact that it is symmetric allows us to calculate this thing. This would be this allows us to calculate the stretch much more easily. So this would turn out to be some positive number usually. It can be greater than 1, it can be 1, or it can be less than 1. What does this number turning out to be 1, what does that mean? Undeformed, meaning that this black curve at that point remains undeformed. Only at that point. At some other point it may have some deformation. Okay, but at that point, if I get C acting on n, dot with n, That's a tensor acting on a vector, gives me a vector. That vector dot with another vector gives me a scalar. Okay, so lambda equal to 1 does mean that there's no deformation at that point in that direction. In some other direction, there might be deformation. Less than 1 means curves getting shorter in that direction at that point. Greater than 1 means curves getting longer in that direction at that point. So indeed, all of that, it has some physical meaning in terms of stretch at a point in different directions. So the C turns out to be a very fundamental quantity. Using the C, we can define a Lagrangian strain, and this is all for finite deformation cases. We are not making any small deformation assumption. You remember when we were dealing with Lagrangian strain as one of the possible definitions of strain, this Lagrangian strain we said was half of final length square minus initial length square divided by initial length square. It came out to be half of lambda square minus 1. So we defined an average measure of strain for this body. Using the exact same strain measure, we can define a Lagrangian strain in the direction n at that point in the same exact way. And it will be equal to half of lambda square, which is nothing but n dot with C acting on n, that's lambda square, and minus 1. So if somebody gives you a body, tells you a curve inside that body, tells you a point on that curve, you can find the stretch on that curve in the direction of the curve using this expression, which is what I did for one of the homework problems. Okay, I asked you to find the stretch so that you can integrate that stretch and find the final length. We can easily generalize this concept by defining the Lagrangian strain as half C minus I. Okay. Which simply, if you go by the definition, it's of C, it's nothing but half of F transpose F minus I. So this is a strain measure. We had a map. From the map, we defined F. That was a deformation gradient tensor field. Using F, we defined C. C was again a deformation tensor field, but it was symmetric. And I'll show you why it's important. And using C, now we have defined strain. So map, then F, then C, then E. That's sort of the flow of kinematic quantities, that flow of the logic really of how we define strain in any arbitrary direction in a given three-dimensional body with a given deformation map. All right, let's take a look at why this can be treated as a strain, as a measure of strain. We'll go back to this interpretation of F, that is a black sphere of undeformed tangent vectors in arbitrary directions. So these are all possible black spheres. If the F tensor field, if all that it does at a particular point is that takes all that black sphere of arbitrary vectors and rotates it to a different location without changing its length in any direction. Okay, if that's all it does, then strain is equal to 0. Yeah, that's right. So if the undeformed tangent vectors are only rotated to the deformed tangent vectors, then we are not changing lengths of any of those vectors, which means that the stretch is equal to 1, and F in that case would be some orthogonal tensor, right? It would just be rotating, just a rigid body rotation of that neighborhood of points. And in that case, there would not be any strain at that point. Let's see if we can understand that a little better. So let's consider any undeformed tangent vector dz. That dz dot with dz is its square of its magnitude. Okay. Its corresponding mapped vector is dx. Dx dot dx would be the magnitude of the deformed square of the magnitude of the deformed tangent vector. Using this basic tensor operations, I can write dz as dz dot with I dz. There's nothing but I multiplied by d. I acting on dz is dz. For dx, I'll replace that with f dz. That's the definition of f. This also is definition of f. I'll use the definition of transpose to write it in the form dz dot with f transpose f dz. And then I'll take this I to the right hand side and I can write it as dz times f transpose f. I goes to the other side, gets a minus sign, and dz equal to 0. Should that be a scalar, a vector, or a tensor? That's 0. Scalar, because this is a tensor acting on a vector gives me a vector, dot product with a vector should give me a scalar. So this quantity that we have in the brackets here, in the parenthesis, c minus I, this will be equal when this acts on any undeformed tangent vector, dot with the same tangent vector. What is this entire thing on the left hand side? Can you tell me? Or maybe what is this entire quantity on the right hand side? Can this be interpreted as n dot with c acting at n? Is it? Right? We just said that this is equal to the square of the stretch in the direction n. Correct? This square of the stretch would, if that is equal to 1, this would be 0 because we subtract that identity from here. So c minus I is a tensor that would be 0 if the deformation at that point amounts to taking undeformed tangent vectors and rotating them to find the deformed tangent vectors. If there is a rigid body rotation in the neighborhood of a point, then this quantity c minus I would be 0 tensor. And that's the ideal definition of strain. That if there is rigid body rotation, we don't want any strain to occur. Or our definition our definition of strain should not produce something non-zero if there is only rigid body rotation in the neighborhood of a point. It can be translation, no strain. Rotation and translation, no strain. But if there is deformation, then this quantity would not be 0. Then this black sphere of undeformed vectors would not go to a blue sphere of deformed vectors, it would go to a blue ellipsoid of deformed tangent vectors. Okay, so c minus I is definitely proportional to strain, and that is why we defined the E in terms of c, and that factor of half is just to make it consistent with your engineering definition of strain, that was delta L over L. You will see that delta L over L is a special case under the assumption of small deformations. This will give you that definition of strain. Okay. And yet again, we can do the exact same process in the reverse side also. So up here, I had undeformed tangent vectors on the left and the deformed tangent vectors on the right. Same thing here. But instead of writing dx as f dz, I'm writing dz as f inverse dx, right? Which is nothing but saying that the inverse tensor would be f inverse. F takes dz to dx, f inverse takes dx back to dz. So that's dz, and on the right I have dx dx. If I go through the same procedure, I come up with a tensor f times f transpose inverse. F times f transpose inverse is called the left Cauchy-Green deformation tensor. Up here, you remember C was the right Cauchy-Green deformation tensor. That was f transpose f. F transpose is also symmetric, but it's a left Cauchy-Green deformation tensor, sometimes called Almancy tensor or finger tensor. People denote that with B. And again, this quantity I minus B inverse is proportional to strain. So another definition of strain is I minus B inverse and factor of half. That's the Euler-Almancy strain. These are two different ways of looking at the deformation at a point. One is taking undeformed tangent vectors to the deformed tangent vectors. The other is the reverse, deformed tangent vectors to its undeformed locations. We are primarily going to be dealing with the right Cauchy-Green deformation tensor. Right Cauchy-Green deformation tensor and the corresponding Green-Lagrange strain tensor. But you should be, of course, aware that there are other measures of strain even in finite deformations. Okay. So this is why this quantity F transpose F is important, not only because it is symmetric, but because it gets rid of any deformed, any rigid body rotation. And it allows us to formulate a measure of strain that would not give you strain if there is only rigid body motion. Okay, so that takes us overall from a map phi. If I give you a map, if I give you a body, if I give you a map, from that map you can calculate F tensor field. From that F tensor field you can calculate C tensor field by doing F transpose F. From that C you can calculate the strain tensor field E. Okay, so so that's sort of the overall flow of how you would do this kinematic computations. Let's take a look at some examples. Back to this map of translation. We had x is equal to z plus u. We found that f is equal to identity, which implies that c is equal to F transpose F, which is what? Identity transpose is identity. Identity acting on identity is identity. So C is an identity deformation field. No surprise there because there is no deformation in this translation. What is E? Half of C minus I gives me 0 tensor. Right? It tells me that there is no strain anywhere in the body. It's just a simple translation. So no strain. That's good. F for the uniform expansion we found was alpha times identity, which means that C is equal to alpha square I. Alpha square I is the C deformation, Cauchy-Green right deformation tensor. And using that, we can find E, which is half of alpha square minus 1 times identity. Oops. Right. So this says that the strain field is constant everywhere in the body because it does not depend upon Z. So it's the same strain everywhere in the body. And the strain is given by half of alpha square minus 1 in all directions because it's a uniform expansion in all directions. Half of alpha square minus 1. Have you seen that quantity somewhere? Half of alpha square minus 1. That's right. That's the one-dimensional equivalent of the Lagrangian strain, half of lambda square minus 1. So alpha in this case is acting as the stretch. Alpha is the stretch in each possible direction, right? Okay. There are some very good examples in the book also. I thought might be worth repeating it. One is the example of a simple shear. Okay, so I think if you read the caption here, it says simple shear. Simple shear is different from something called pure shear. There is one thing simple shear, there is pure shear. I'll talk about pure shear later. But simple shear is where you have a body that looks like this, a square domain, and you simply shear the top to the right by some amount beta. That's a simple shear. A map that gives this deformation is this, that Z1 plus beta Z2, E1, Z2, E2, Z3, E3. So there is no deformation in the Z2 direction and the Z3 direction which is coming out of the plane. There is no deformation in that. But in Z1 direction, I'm getting some deformation which is given as Z1 plus beta Z2, which means that when Z2 is 0, I have no deformation. It's Z1, E1. as Z2 increases, as I increase up in height, the horizontal displacement in the even direction increases by an amount beta. That's how to interpret this map. So as I go up in Z2, the horizontal displacement of the corresponding line increases proportional to beta. And okay, so I'm out of time here, but let me quickly do this F, and then I'll let you read the rest of them. F would be what for this map? The first term, partial with Z1, 1. First term, partial with Z2, beta. First term, partial with Z3, 0. Second term, Z1, Z2, Z3, 0, 1, 0. And third term, Z1, Z2, Z3 would be that. I've already computed F transpose F for the map. That's given C. And what would be E? C minus I, right? C minus I is nothing but removing 1 from the diagonals. So I get, and half factor is sitting outside, so I don't need to worry about that. 0, beta, 0, beta, beta square, 0, 0, 0, 0. That's the strain tensor. Note first of all that F tensor, C tensor, E tensor, they are all constant. They are exactly the same tensor in everywhere in this body, which does not always happen, but this is a uniform tensor field. Okay, so let's stop here and I'll come back and try to continue this topic. See you all on Friday.